Hey guys, time to do an example of Newton's first law, I guess. This is the type of analysis we're going to do all year. It's a purely conceptual and qualitative analysis, and I hope this makes sense. I'm going to try to keep it short, but sweet. So this is going to be related to the next thing we're going to do, which is simple harmonic motion. So let's introduce the concept of a mass on a spring. When you have a mass tied to a spring, there's a equilibrium position. The equilibrium position is where there is no force. That means the spring is neither stretched nor compressed. And we'll say the block, some mass has mass m, we'll say no friction, of course, to make our lives easier, right? If I pull the mass this way, the force points this way, which we'll say is negative. We'll say this is a positive value of x, and we'll say this is negative. So left will be negative, right will be positive. We'll establish that. Obviously, if I push the block this way and the spring is compressed, it'll be positives. The force for a spring is therefore equal to negative kx, where x is the displacement vector, right? And the negative just means it's opposite that vector. So positive x gives you a negative f, a negative x gives you a positive f, right? So we call this a restoring force. Is the negative sign, which means it always points back to equilibrium. Cool. So here's your challenge. So that's it. Right, that's the setup. Your challenge is this. Uh, let's pull the block to a positive, what we call amplitude. And we're going to talk about this next week when we talk about energy. Um, but we'll just say we pull it to here, and instead of just some random x, we'll call that A, like the maximum value is amplitude. Great, and you let it go. You let it go at rest. But that's just for an instant moment. Clearly, the spring, just like dropping a ball, clearly it's just going to instantly move, accelerate to the left. But then what happens, right? So you're going to map meaning you're going to outline in detail the acceleration, velocity, force, uh, as it moves over time, right? And you're going to graph. Well, I don't know if I want to graph them yet. Let's just outline it conceptually over time. We'll graph it later, right? Meaning, when is it speeding up, right? When is it slowing down? You're going to want to draw F and V vectors at key points, right? When is it slowing down? When is velocity maximum? When is velocity equal to zero? Right? When is acceleration maximum? When is acceleration equal to zero? In other words, what is the entire motion look like and why? Boom. Let's do it. All right. Next page. So let's just draw a diagram of x equals positive a. We're going to label f and v. Remembering that f net is acceleration conceptually. We also know that because this is horizontal, that gravity and normal force cancel, and therefore the only net force is the spring force. So F net is the spring force. So that makes our lives really, really, really easy. So we start out at v equals 0, and we start out at some negative f. Cool. That means we have a negative acceleration. Negative, careful. Negative doesn't necessarily mean slowing down. In this case, negative means speeding up. So initially, we'll call this point one. So we have our diagram, and then we have like our list. All right, this is what I call a map. We have a diagram and a list, right? Mapping, just like you would say, I said map your trip to California, right? You would say, I did this, and here I am, and I did this. You would have a diagram and you have a list. Here's what I'm doing. That's what I mean by map. I like that word, right? That means you outline, say what's happening, and you draw it, right? So, one, velocity is zero, F is negative, which means left, right? So A is negative. So it speeds up left. This is key, guys. Negative does not mean slowing down. Ah, it never did. Never ever did it do that. Right? If for some reason you change yourself, you got to untrain yourself of things that are just completely incorrect. Right? That is not what negative means. Negative is a vector direction only. If I'm speeding up to the left, that means I have a negative acceleration. That does not mean I'm slowing down necessarily. Right? Obviously, if I'm moving in the positive direction, and A is negative, then I am slowing down. But this just means left. That's all this negative sign means. Point two, I would say, is maybe in the middle after it's reached some maximum speed. So it reaches a maximum speed because at that moment the force is zero. It does not stop. I'm going to leave that as an exercise for you. Why does it not stop there? That's one of the most important parts that we're going to do. So point one here, point two here, the velocity hits a maximum. Why? We'll explain that in a second. The force is zero because we're at equilibrium, right? Therefore, the acceleration is zero. Does not stop. I'll give you a hint. Newton's first law, right? Newton's first law says if F is zero or F net, and this is F net, right? If F net is zero, velocity is, let's you fill in the rest. Good old Newton's first. It's the first one. Classic, right? Don't forget the Newton's laws and observe the universe, right? Things don't just stop on their own, right? You need something to stop them. And if there's no force to stop it, it doesn't stop. Don't invent physics just because your brain thinks it's true. Most of the things our brain thinks are true are not true. That's why we're meticulously aligning our logic so that our brains align with accurate truth. Isn't that amazing? Our brains tell us lies like all the time. Let's see if we can undo them together, right? I know, humbling, right? Take a moment. It's cool, right? I just had it. Like it's so good. All right. Anyway, point three is over here. So point three is where it's point three. I don't know. I think I want to do in the middle here. Point three in the middle where it slows down. Why does it slow down? Well, it's moving to the left, which means it has a negative velocity, but the force is now to the right. Those are opposite. That's why it slows down. Here's why. The why. Boom, right? Is that I have a velocity to the left. Let's change colors here. I have a velocity to the left. Boom, right? But I have and here, I guess there could be another point here, right? Where we have a negative velocity, negative force. That's speeding up, right? Negative velocity. Ah, negative velocity, negative force, right? Just means left. So this is speeding up. They're in the same direction. They're both left. They're both negative. Here I have a negative velocity, positive. That's why. So since it was slowing down here, clearly the reason why is because F flipped from F flipped Sorry, my pen's being weird. I'm trying. Here we go. Negative to positive. Positive meaning right, not accelerating, right? So we have an acceleration to the left. Now we have a deceleration to the right. That's why. That's why this is maximum in the middle. It's because at point two, we have a Vmax because the force flipped from negative to positive, right? I feel like my diagram could be a lot more clear. I'm going to clear this up in a moment in correspondence to this. I'm just running out of space. Here, let me do that on the next page. This could be way better, right? So we have step one, velocity is 0, right? Force is max, acceleration is max, right? And this is at x equals positive a. Really, I should have said point two, but I'll call it point 1b, right? V is negative, A is negative, F is negative, which just means left. We have a negative velocity, and this is here, sorry. X is positive A, right? Here we have negative F, but velocity is 0 just for that split second, right? Here at point 1b, which was in the middle, I should have called that point 2 in retrospect, right? I'm going to draw that like this. Notice what I'm doing, and I should have probably been a little bit more clear here. I'm drawing a diagram. Here's x equals positive a. This is point 1b, where we have a negative f and a negative v. So it's speeding up. This is a little better. Point 2 is in the middle, where we have v max, f equals 0, right? Because right after point 2, right, this is still x equals 0, x equals positive a. We're going to notice what I'm doing is I'm labeling my points and I'm drawing my vectors. F flips direction at point 3, right? So v max, f equals 0, right? An object in motion stays in motion because this means velocity is constant. That was the answer to the question before, in case you forgot Newton's first law, right? F flips direction, right? From negative to positive. This is a complete analysis that we're doing right now. Since it flips, afterwards the velocity is to the left, but the force is to the right. So V slows, right? V is negative, which just means left. A is positive, F is positive. So it slows down. We have a negative velocity and a positive force. Great. Point 4 would be over here at x equals negative a, where it slows down to a stop. It stops. F is maximum, right? Right? And positive. A, therefore, is maximum and positive. And that means step 5, it goes back the other direction. X equals negative a. A fun trick we're going to do, a fun game we're going to do is realize that the acceleration equals the deceleration, therefore it goes the exact same distance. We're going to prove that with energy next week, but for now we can just conceptually say that. Maybe I'll sort of show that at the end, which I think is useful. Here we have a positive velocity and a positive force, just meaning to the right, so it speeds up. Make that blue. I'm going to move to the next page to do the next few points. Call this point 6. What is point 6 going to be? Point 6 is back in the middle where we have a positive velocity max. F equals 0. It went to negative a. It's now at x equals 0. X equals positive a. I'm sorry for the script. My thing got a little wobbly, but I think we'll be okay. F flips direction here from positive F to negative F, right? Because after it moves to equilibrium, it's now going to move to the right. So notice what I'm doing is that I'm meticulously showing what's happening to each quantity. Here I know it's moving to the right, but I know the force is to the left. So it slows down, right? Because these are opposite each other. And then finally, 0.8 is the same as 0.1. It returns back to the original position and stops, right? Because here the force accelerating it is the same as the force decelerating it. Here's where I'm showing this. Because it's the same force, same acceleration, uh, uh, for positive F and negative F for the acceleration and the deceleration. Therefore, and by the way, 3 dots means therefore, distance delta x, the displacement, is the same, right? Because it went from rest. So it went from rest to V max to rest again. If you have the same acceleration positive as you have deceleration negative to the left, then you're going to go the same distance, right? If I accelerate at 5 meters per second on average, and that's average, we should say average, same A average for this because with the average, the acceleration's decreasing and then increasing, but it's the same acceleration on both sides on average. So maybe an average of 5 meters per second on this side, an average of negative 5 meters per second on this side. So we go the same distance. That's why we know it goes from negative A to A and then A to negative A. And then repeat. And that, my friends, take that in. Right? Go back through. That one got a little messy. Yeah, that got a little messy. Right? We can go back through the steps. Here's really the steps. Step 1, step 2, we should call that step 2, step 3, step 4, step 5, right? All the way through. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Really, we end up with 9 steps that are key to our motion here. And then it just repeats forever. And if there's no friction, I know in real life it would slow down, right? Each iteration, it would go a little less far. It would lose some energy because of whatever friction force. In fact, we're going to have a little quiz on that at some point. Because if we add friction, we can calculate like how much force and energy it loses. We'll do energy next week. But force and velocity tell us the whole story. How force changes velocity from Newton's first law. We use vectors to figure that out. Careful, guys. Negative is a direction, right? Positive is a direction for vectors. Hugely important. I hope all of that made sense. This is the type of analysis we're going to do. That is a conceptual mapping of force, velocity, and acceleration for a mass on a spring. See you guys later.